Yeah, welcome to this webinar on non-directional overcurrent protection. My name is Björn Ciala. I will do the presentation on this webinar training for you. To the agenda of this training. We will start with a short introduction on electrical faults in the network. Then we will continue with basics of overcurrent protection. And later on, we will focus on the definite time and the inverse time overcurrent protection. Afterwards, it's going to be the high current stage, and at the end, we will have a look at the protection testing principles and also on limitations and alternatives to overcurrent protections. So let's start with the first thing, electrical faults in the network. Here, as an example for you, is a medium voltage network. You can see it is one transformer injecting into a medium voltage network, which is, for example, 10 kV. And we have multiple feeders connected to our bus bar. And we want to have a look at one feeder, which is a radial feeder. Here you can see we have our main bus bar with the in-feed, and we have small substations on the line that have distribution transformers which supply then the low voltage network. So the customers are connected to these distribution transformers here, here, and here. So what happens in case of a fault? If we have a fault, let's say here, almost at the end of the line, then there will be a high current flowing towards the fault location. You can see the current will flow through the transformer into the medium voltage network and then through our faulty feeder up to the fault. Okay. This fault must be switched off, but it doesn't need only to be switched off, it needs to be switched off fast and selective. Well, fast is pretty easy, it should be switched off as soon as possible. But what does selective mean? Well, selectivity means that only the faulty line segment will be switched off. And in this case, then you will be able to maintain the power supply of as many customers as possible. So to further showcase this, let's have a look. If we open a breaker here, or if you interrupt the current at this part, or at this position, then you can see everything that is gray is disconnected from electricity, which means that also the customers here, here, here and here are disconnected, and therefore they don't get any power supply. So in this case, this is an unselective trip. A selective trip would be a trip here, which means that only here at this position the line is interrupted, or the current path is interrupted, and that means that yes, the customers here will not be supplied, but at least it will be possible to supply the customers here, and here. So this is the goal of selectivity, to interrupt the power supply of as few customers as possible. Okay. How can we switch off such a fault? How can we disconnect the current flow? Well, there are different possibilities. Fuses are one of these possibilities. Fuses are one of the most common things in the network. The advantages of these fuses is that they are inexpensive and then they can reach fast trip times. So fuse means that there is an electrical lead that melts down if the current is too high. And as soon as it melts down, the current path is interrupted. So if the current is too high, then the current path is interrupted, so it needs to be made sure that a load current will not trigger such a fuse, but only fault currents. And with this, you can achieve pretty fast trip times. But the problem is that these fuses can only be used once, and they have a somewhat limited range of use. For example, for a 10 kV network, it's approximately 200 amps, and for a 20 kilovolts network, it's about 100 amps. On the other hand, to fuses, we have the possibility to have protection devices. Well, how does this work? We have a current measurement with a current transformer, or a CT. This current transformer transforms the high current of the network down to secondary values, which then can be used by digital or electromechanical devices. And these secondary currents will then be injected into a protection device, which is resembled by this box here. This protection device measures the current and then defines or does the trip decision. So it decides, is there a fault or not? If there is a fault, then it decides, should I trip or not? And as soon as this device found the trip decision, then it can give a trip signal to the circuit breaker, which is here. The circuit breaker in the end is an asset that interrupts the current flow. And the circuit breaker is able of breaking also short circuit currents, compared to, for example, load switches, which are not able to interrupt short circuit currents. And the advantages of these protection devices is that they can be used multiple times. So you can switch off and switch on the circuit breaker again and again and again. And also it is a very flexible setting. Usually these devices are nowadays digital devices, and here you can put in almost any imaginable setting to define when the relay should trip or not. The disadvantage of these protection devices is that they are more expensive and also that they have higher maintenance costs. So the whole system, so the current transformer, the protection device and the circuit breaker, they all together are the protection system, and this protection system has to be maintained on a regular basis. So from time to time, let's say every 2, 3 or 4 years, you have to go there and check whether everything is working correctly. Okay, now to overcurrent protection itself. The definition of the overcurrent protection is pretty simple. The protection system operates if the current exceeds a set value. So you can define a value, and if the current is above this value, then the protection system operates. Well, there are two different kinds of overcurrent protection. Typically, you have on the one hand the definite time overcurrent protection, which is also called DT, for abbreviation for definite time, or with the ANSI code, it is ANSI code 50. This definite time overcurrent protection always operates with the same trip time if the current exceeds your setting value. And this trip time can be defined also as a setting. So if the current is above your threshold value, then it always trips with the same time. On the other hand, you have inverse time overcurrent protection, or IDMT characteristics. IDMT is for inverse definite minimum time characteristic. These inverse characteristics are also defined by their ANSI code, which is ANSI code 51. And these operate if the current exceeds a setting value, but the trip time in the end depends on the current or depends on the magnitude of the current that flows through the protection device. It means that if I get a higher current, then the trip times will be faster. If the current is a bit lower, then the trip time will be longer. Well, there is a huge amount of different inverse characteristics that can be used, but typically they are standardized. So in this case, you can see we have, for example, standardized by the IEC, different characteristics, the standard inverse characteristic, the long time inverse characteristic, the very inverse, and the extremely inverse. I also show here the formulas how to calculate the trip time based on the standard. Depending on where you are on this world, there are different standards. So, for example, the IEC standard is commonly used, let's say, all over Europe. But in contrast to that, there are other characteristics like the IEEE or the ANSI standard, which are a bit different to the IEC standard. And that also is shown in the formulas. So even if the characteristic is called very inverse, you still have to have a look at which standard is meant with this. So if it's the very inverse standard of the IC standard, or maybe the very inverse characteristic of the ANSI standard. Okay. For further explanations, we start with the definite time overcurrent. Let's have a look at the operating characteristic. Here you can see the operating characteristic looks pretty simple. This is the axis of the current, and this is the axis of the time, of the trip time. So if the current is below my threshold value, I greater, then nothing happens. Then the trip time is infinity. But if the current is above my threshold value, I greater, then the relay trips with a trip time which is called the time of I greater. So I have two different settings. The first one is I greater, the pickup current, and the second one is the time delay, Ti greater. If I change, for example, the pickup current, then this shifts the characteristic to left or to right. So if I decrease the pickup current, then the characteristic is shifted to the left side, and if I increase the pickup current, the characteristic is shifted to the right side. The same happens with the time delay. If I increase the time delay, then the characteristic is shifted upwards, and if I decrease the time delay, then the characteristic is shifted downwards. So now the question is, how do I set such a definite time overcurrent protection? Let's have a look at a radial feeder, which is shown here. For the beginning, for the setting of the first relay, you start with the last protection device of this radial feeder. So you have a look at this protection device here. This is what we want to focus on. So now we must define settings for this pickup current and for the time delay. Let's start with the pickup current. This must be above the maximum load current and below the minimum short circuit current. So we have two different states of the network. We have the normal state, which is the healthy state, where we only have load currents, and we have the faulty state, where we have fault currents. And to make sure that we can decide between a healthy or a normal state and a faulty state, we need to make a current setting between the highest possible load current and the lowest possible fault current. So in our case, let's say the maximum load current is 300 amps over this line, and the minimum short circuit current is 1 kiloamp, so 1000 amps. That means we have to define our setting of I greater, our pickup current, somewhere between these two values. And in this case, we choose 420 to have at least some distance between the maximum load current and our setting to make sure that there is no overreaction on the protection system in case of a current close to the maximum load current. Okay, so now we have our setting for the first value, I greater. And what we then need is our setting for the second value, for the time delay. For the time delay, we say, well, the setting must be longer than downstream trip times. So for example, if I have a fuse or a protection device for the distribution transformer at this bus bar here, then I need to take this into account. And then in this case, I would, for example, say that the trip time of the protection device here is 100 milliseconds. So if there is a fault inside the distribution transformer or downstream to this in the low voltage network, that only the fuse here trips and not the protection device here. This is made sure in our case with the setting of 100 milliseconds. So this is for the first protection device in this radial feeder. But what is with the other protection devices here, with the protection device in B and in C? Well, for this we have to do protection grading. That means we need to do a coordination of the protection settings between the surrounding protection devices. That, for example, the protection device B here must be set with taking the settings of the protection device here in C into account. And that is typically done for overcurrent protection with time grading. Why do we use time grading? Well, if you use definite time overcurrent as a line protection, so to protect our overhead lines or cables from electrical faults, then the setting I greater cannot be used to differentiate between a fault on between the fault here or here or here. Oftentimes the fault currents do not change that drastically if they change the position on the overhead line. So for example, if I measure the current here and I have a fault here or here, it doesn't necessarily mean that the currents or the short circuit currents are that different to each other. That means just by having a look at the current, I cannot tell where my fault position is. So the current itself in this case is not enough to differentiate or to distinguish where the fault is. And therefore we set the same pickup value for all the relays. You see the relay at B and the protection device at A all have the same pickup value for the current. Now, in order to achieve selectivity, we do a time grading. So that means that the protection device of the upstream line segment has a higher trip time than the one before. So we started with the settings here with 0.1 seconds. This is our first setting. And now the upstream relay gets a higher trip time. How will it work in the end? Well, if we have a fault here on the segment between C and D, then this fault will be seen by all three relays here. So the relay in C, in B, and in A. All of them see the fault, but all of them have different trip times. So if there is a fault here, then this relay here in C will have the shortest trip time, and therefore it will disconnect the fault first. And after this relay has disconnected the fault, these relays here and here don't see a high fault current anymore, so they will drop off. As they drop off, it means that they will not trip, so that they will remain stable, and a power supply for customers connected to the bus bar C and D is still possible. And the same, and now if I have a fault between D and C, if I have a fault here, then this relay does not see anything because the fault is injected from here into my feeder. So the relay at C will not see anything. The relay at B and at A will see the fault current. They will pick up. But this one, the relay at B, is the fastest to trip. So this will disconnect the fault. And so once again, selectivity is reached. So by increasing the trip time step by step with every relay, we achieve selectivity. Now the question is, how long should this trip time typically be, or this time delay between two relays? And typically these settings are between 300 and 500 milliseconds. This needs to be a certain time between, because the pickup time of both protection devices need to be taken into account. Also the inherent delay of the circuit breakers. So also the circuit breakers need some time to react. Also the tolerance of the time measurement within the protection devices, and also some time delay of intermediate auxiliary relays or something like this that would be in between the protection device and the circuit breaker. So depending on how much time you have to take into account, you choose some value typically between 300 and 500 milliseconds. In our case, we choose a value of 300 milliseconds. Okay, so now we know how the definite time overcurrent is set and how the time grading really works. But we did not focus yet on the inverse overcurrent. So let's have a look at the inverse overcurrent characteristic. Here you see the tripping characteristic of such an IDMT curve. And you see the faster the trip, the faster the current here, once again the current here and the time here. And the higher the current, the longer the trip times. So if we have a look at this, if the current is, for example, 500 amps, we get a trip time of approximately 20 seconds. If the current is, for example, at 800 amps, then we get a trip time of between 4 and 5 seconds. So you see, the faster the higher the current, the faster the trip time. That's the rule for inverse characteristics. What settings do we have? The first setting is one of the most important. It's the characteristic type. Should it be a normal inverse characteristic, a very inverse characteristic, and so on. This is defined then by the formula that is used to draw this inverse graph. Then once again I have pickup value, which is typically called IP, and time multiplier setting, also called TMS or time dial, or TD, whatever. There are many different names for this. And those two influence the position of our characteristic. So with a change of the pickup value, my characteristic shifts from left to right. And with a change of the time multiplier setting, the characteristic is shifted up or down. Okay. How do we set this then? Well, once again, we start with the last protection device in a radial feeder. So once again, if you remember the picture of the radial feeder before, we start with the last of the relays. And first we select a characteristic type. And this characteristic type usually depends on the downstream asset or protection system. So for example, if there is a fuse, for example, that should be emulated by the inverse characteristic, or if there is a motor with overload characteristics, that should be also taken into account by the upstream protection devices. That all have an influence on the characteristic type of the inverse characteristic. And if then this is defined, for example, if you define, well, we choose an IAC very inverse characteristic, then you start to set the pickup value. And once again, the pickup value is defined by the same way as it was for the definite time overcurrent. So you need to find a value that is between the maximum load current and the minimum short circuit current. If we have the same setup as before, then we once again can go with a pickup value of 420 amps. And then afterwards, the time multiplier setting must be defined. And this must once again be coordinated with the downstream protection system. For example, with a fuse or protection device, and it must be made sure that there is no overlapping of the different characteristics. Typically, then you draw the different characteristics of the different protection devices into one diagram and see whether one curve cuts through the other curve. And you just need to avoid that one cuts through the other curve. So if this happens, then you need to change some settings in some relays. Here you can see one specialty for digital inverse time overcurrent that is shown in this characteristic here. If you have a look at this part here, we have a setting value of 420 amps, but the real pickup does not start at 420 amps, it starts somewhere above. In this case 1.1 above this value. And this is typically built into digital relays to make sure that they will not pick up with extremely extremely long trip times. Oftentimes this factor is built into a relay. For example, 1.1 is something that you oftentimes cannot change, but depending on the manufacturer, it could be 1.05 or 1.2 or something in this area. But just be aware that not typically digital relays will not directly operate at the pickup value, but somewhere above, just to avoid very, very long trip times. Okay. Now, how do we do our time grading? Well, once again, we have an overcurrent protection, so a current pickup can not be used for grading over our line that is here, or over our complete radial feeder. That means that we need to make sure that all of the protection relays in this feeder have the same characteristic and also have the same pickup value. That makes sure that there is no overlapping. And here you can see a characteristic of these three different overcurrent or inverse characteristic relays. And once again, we do a time grading of the upstream protection, and the time delay between the downstream and the upstream protection relay must be long enough, must be the same rule as before, between 300 and 500 milliseconds, but the question is where. And here you choose the setting with the highest possible current, which is the maximum short circuit current. The highest possible current leads to the shortest possible trip times, and so you choose the shortest possible trip times, and there the time difference between both sides must be at least 300 to 500 milliseconds. And with this you can do your time grading, and then you know that there is enough space between the characteristics and you can do your overcurrent grading. Here is, for example, different time multiplier settings with 0.3, 0.5 and 0.8. Okay. Now to another pretty interesting topic, the high current stage. Let's leave aside the inverse characteristic for a moment and have a look at the definite time overcurrent characteristics. If we look at this, here we have our settings of our protection devices in the feeder. And now if we have a look at the short circuit currents, we see that, for example, the short circuit currents will get bigger and bigger the closer we will get to our in-feed or to our bus bar A. So the real short circuit, the real short circuit current is somewhere between the minimum and the maximum short circuit current in this curve. So somewhere in between will be the real short circuit current depending on the location of the line. So you see this here is location directly in front of bus bar A. Somewhere here is at location B. This is the fourth location at substation C. So these are the currents here. And the currents at the end here are at the substation D. So that will lead to a problem. If we have a look at the trip times here, faults that are between A and B will be disconnected with the longest trip time in this whole feeder. So in this case, 0.7 seconds is the longest trip time of my trip times. This can be even longer if I have more feeders with more segments in between. Then the trip times can go up to 1.5 seconds and longer. That means we have a long trip time directly for faults directly in front of A. But the fault current directly in front of A will be very high. As you can see, the closer we come to the bus bar A, the higher our fault currents get. This leaves us with the problems. The currents with the highest magnitude will have the longest trip times. This will lead to stress on the equipment, on the transformer, on the bus bar, on the cables, on everything in the current path. And this is, well, a best case scenario would be that we can avoid the stress on the equipment and can disconnect faults with a very high current faster than it would be typically possible. And in order to do this, we introduce a second stage, a high current stage. So additionally to the first stage that is set into this relay here, we use second overcurrent stage with a higher setting but a faster trip time. In order to maintain our selectivity for if we want to set our relay in substation A, then we take the maximum short circuit current at station B. Take this maximum short circuit current, let's say in this case it's 2.7 kiloamps, and now we select the current that is above this value with a certain safety margin. So our setting for the high current stage could be, for example, 3.2 kiloamps. So now with this setting, if the current exceeds this setting, then we definitely know that the fault must be on our line between A and B. There is no other possibility for a fault to be above this current. Let's say if I have a fault current somewhere between B and C, then you will see even with the maximum possible short circuit current, I will not be able to reach this threshold. So with this method, we now have a second stage that enables us to disconnect high current or very high current faults faster. Because now, if I know that there is no reason for any, if I know that the fault must be between A and B, then I don't need to wait any much longer for any other relay to react or something like this. That's why I can go with a very, very fast trip time. In our case, we typically choose between 0 and 100 milliseconds. So in our case, let's say 50 milliseconds as time delay. So a high current fault that is very close to our relay will be disconnected now much faster, which avoids a lot of stress on the equipment. The resulting protection scheme or the resulting overcurrent protection characteristic will now look like this. This is a two-stage overcurrent protection. Here you can see the first stage with a lower pickup value but a higher trip time, and then the second stage, our high current stage, with a high pickup value but therefore a very fast trip time. So with this we are able to disconnect faults which are very close to our protection system or very close to our bus bar faster. The same rules can be used for inverse characteristics, so the same also applies for inverse characteristics. I could have a characteristic which goes in an inverse way like this here as well. Now to the point of protection testing. So now we finished how to set the relays, but the protection devices need to be maintained as well. And one part of this is protection testing. Because it is not enough to just build these protection devices into your network. You need also to make sure that everything is running correctly. You need to make sure that the system is still able to operate. Because there are very, very high requirements on protection devices. If they are mounted in a network, they have to be there for several years, for example, without doing anything. They must not do anything. But when there is a fault, they must react very fast. So within a few milliseconds. That are very, very that is a very, very challenging problem for the protection relays, and you typically don't find out whether something goes wrong until you have a fault and something really goes wrong. So you don't know if a relay is not working correctly anymore. So in order to avoid like misoperation during a fault, you need to test the relays. And typically you decide between two different tests. The first tests are the commissioning tests. These are typically done when the relays are set into service. When the relays are just built up in a new substation, then you do a commissioning test. Also, you typically do a commissioning test if you do extensive parameter changes, if you adapt the characteristics and so on. Then you would do a more detailed test, like a commissioning test. And after this, typically there is a test in periodic cycles, which is called routine testing. And this, depending on the utility where you are, is between 2 to 4 years as a cycle. So every 2 to 4 years, every relay needs to be tested. But oftentimes these routine tests don't necessarily need to be that extensive as the commissioning tests. So how do you test then the relays? Well, you inject currents and measure the signals back. So basically you have a test set here that injects a current into the protection device. And the protection device reacts whether it trips or not, and the trip reaction is measured back by the test set. So then in the test set you can define, well, for this and this current I got this and this trip time, so the relay is okay. Typically all settings in the relay have to be tested, which leaves us with different settings. The first are the pickup settings, I greater, and I pickup. This is typically done with pickup tests. So you start with a smaller current and then you increase the current step by step in small steps until the relay picks up or the relay operates. And then you compare the result of this current with the nominal value, so with the value that should have been in the protection device. And if they match, then it's okay. If they don't match, then there's a problem. If everything works with the pickup test, then the second test is the trip time test. With the trip time test, you check whether the timing settings work correctly. So the time values of the definite time stages, or the time values of the IDMT characteristics, as well as the time multiplier setting or the time dial. Here you do a so-called test shot, which means a current is injected that leads to a trip. So you inject a current that is higher than the pickup current to get a trip, and then you measure the trip time. And the result of this measured trip time will be compared with the nominal trip time that should be in the relay. And if they match, everything's fine. If they don't match, it's not that good. For a definite time overcurrent characteristic, it is sufficient to have just one test shot per stage or per element. For an inverse overcurrent stage, you need to have at least, let's say, 2 to 3 test shots on the characteristic to make sure that the time dial and the characteristic, or the characteristic type itself, is set correctly. And if that's the result, then you know your protection device is working all right. Next thing is that also different fault loops have to be tested, because protection devices are digital devices, and oftentimes there is different logic for single-phase faults and multi-phase faults, so 2 or 3 phase faults. So you're not only done with just one fault loop, you need to test different fault loops. Therefore, the test can be done with a single-phase or 3-phase test set. Usually, it depends on what you have at hand. If you use a single-phase test set, then you need to rewire. You need to rewire from a phase-to-ground fault to a phase-to-phase fault in order to get all different fault loops. If you have a 3-phase tested, then there is no need for rewiring during testing. Then you can test each fault loop as you like. And the most important thing about protection testing is at the end of the protection test, if everything is done, you need to do a test report. You need to create or write the test report in the end that notes down that everything is all right. This is more or less to law requirements. Oftentimes it's just necessary by law to have some document that tells whether the protection device has to be tested or not, and also whether the device was still okay or not. So a test report is mandatory. Okay. Well, then let's have a look at the limits of this non-directional overcurrent protection. Up to now, we just had a look at radial feeder. But if the network topology gets a bit more difficult, then we will have problems. As you can see here, we have a ring network and we have a fault here. You see the faults here, so there will be a fault current flowing through this side of the feeder and it will flow through this side of this ring. And now, just based on the magnitude of the current itself, the protection device cannot decide on the direction of the fault. So for this protection device here, it doesn't know whether the current flows from right to left or from left to right. So if I would do a typical time grading with a ring topology like here, this relay would also operate a fault which is here because the current flows also through this direction. So this relay would operate, and if, let's say, this operates correctly, then we still see that this customers here are disconnected. So basically, in a ring topology or also in mesh networks, which are even more complicated, a simple non-directional overcurrent will just not work anymore. Another reason or another problem for the non-directional overcurrent protection or overcurrent protection in itself is a network with changing in-feed conditions or with a lot of double lines. Because if the source impedance, so the impedance of your in-feed or the strength of your in-feed changes a lot during the a few days or during the day or during a week or a month, if this changes a lot, then it can happen that the maximum load current can be higher than the minimum short circuit current. So if the highest possible load current is at one point higher than the lowest possible short circuit current, there is no clear value in between where we can distinguish this is a fault and this is not a fault. So basically there is no reasonable pickup value left in this case, and the normal overcurrent protection cannot be used anymore. So how do we cope with this problem? Well, the first alternative to this is directional overcurrent protection. So additionally to the current measurement with the CT, you also measure the voltages with a voltage transformer or a potential transformer. And based on the angle between voltage and current, the protection device can decide where the direction of the fault current is. So in which direction does the current flow. And with a direction measurement, we now know, or we now can set our overcurrent characteristic in a way that, for example, this relay only reacts to faults in forward direction, so only reacts to faults in this direction. So if, once again, I have a fault here, the current flows through this direction, then the relay sees that it's a fault in reverse direction, so it should not operate. So in this case, this relay is not operating for a fault here, so only this and this relay, and then everything is fine. So this directional overcurrent is mostly used in ring networks. But this also depends on the country. Which protection system is used where is strongly depending on the philosophy in the different utilities or system operators, and also depending on the philosophy in each country. Another possibility or another alternative is the distance protection. For distance protection, we measure the voltage and the current once again, and out of this we can calculate the impedance of our fault loop. For example, this is my relay, and I can calculate the impedance of this fault loop here. So out of the impedance, I can compare it with the typical line impedance, and then I know how far this fault is away from my protection device. Therefore, also I can measure the distance between my protection device and the fault. That's why it's called distance protection. And with this, I can selectively or mostly selectively say the fault is on my line that I have to protect, or the fault is not on my line, the fault is somewhere else. And distance protection is typically used in mesh networks, once again depending on the country. Also oftentimes used in high voltage or also transmission systems. Okay. And last but not least, we have the line differential protection. Here you can see the current is measured at all ends of the protected area. So you see this is our line, and the current is measured here and here. And additional to that, you have a communication between both protection devices. So that means the device here measures its current and transmits the measured data to the other end. And the other end does the same, so it measures the current here and transmits the measured current to the end here. So in each of these end devices, now they can compare the measurements that they have on their own side with the measurements they get from the other side. And if they find there is a difference between both sides, then they can operate. Then if there is a difference, then the current flows somewhere where it should not go, which typically is an indication for a fault. So then they can operate, and the circuit breakers on both sides can trip. Line differential protection is typically used in mesh networks and also for more complicated topologies, such as multiple terminal topologies. If you not only have a 2-terminal line, but a 3- or 4-terminal line, then the classical protection philosophies will become get problematic, and therefore you need something else, like, for example, line differential protection. And well, with this, we are at the end of this short webinar training. And well, if you have any questions, then you can just ask them